In this video, we'll study the derivative shortcut rules for logarithmic functions. In order to come up with the shortcut rule for differentiating logarithmic functions, let's start with the most general logarithmic function, that is logarithm base b. And I'm going to use what I know about the derivative of exponential functions to come up with the derivative of these functions, the shortcut rule. So let's go ahead and do that. Now recall, there's a connection that we know about between exponentials and logs. They're inverses of one another. In particular, this expression is equally written this way. This really means that I take the base b and raise it to what power in order to get my input x, right? So b to the f of x is equal to x. These are equivalent statements, okay? So I've just rewritten this in a different form. And now what I'm going to do is differentiate both sides of this equation. And of course, as long as I do the same thing to both sides of an equation, the equation should hold. Okay, so let's go ahead and do that. So I'm going to differentiate with respect to x on both sides of this equation, d dx. Okay? And this is b to the f of x, and this is x, right? I'm just differentiating both sides of this equation down here. Now, I know the derivative of x. That's easy. That's equal to 1. So I know one part of this already. The other part, again, I know this because I know about derivatives of exponential functions. In particular, exponential functions base b, and of course we use the chain rule definition, right? We've got an f of x up here. So remember, when we differentiate this, we get a natural logarithm, base b. We get the f prime to come down. But we also get bf to the f of x again, right? So this is our expression once I differentiate this side. Now I'm going to use algebra in order to isolate f prime. Because after all, my original f is the logarithm function, right? So if I can figure out what that is, I'll now have the shortcut rule for differentiating logarithm base b. So I'm just going to use algebra. And so when I do that, of course, I need to divide both sides by those quantities there, right, these two values. And I get that f prime of x is equal to 1 over the natural logarithm of b multiplied by b to the f of x. Now, one other thing we have to note here is that, wait a second, b to the f of x down here, this quantity, right, is really just equal to x, right? I have it written there. So I'm going to replace b to the f of x just with x. So when I do that, I finally have that the derivative here of f of x is given by 1 over natural logarithm of v times x. And in fact, here it is. We have the shortcut rule for differentiating a logarithm base b, right? Because that's f of x. That's how we defined it to begin with. Notice that all we did is we rewrote this in terms of exponentials. We differentiated both sides and solved for f prime. Okay? So now I can rewrite this maybe in a more clear way with the derivative of that thing, right? So in other words, I can write this as d dx of log base b of x. Okay, so that's our shortcut rule for differentiating a log base b. But notice that we can also, with this in mind, figure out the derivative of the most famous logarithm function, that is the natural logarithm, right? ln of x. But we do that with this in mind. Let me remind you of something. That is that, remember that by definition, the natural log of x is equal to log base e of x, right? Natural logarithm is defined as the logarithm base e. So in other words, if I take everything down here in my expression that I came up with for the generic derivative, or the derivative, I should say, of generic logarithm base b, if I replace all the b's with the special b, e, then I get the expression for the derivative of the natural log, the most famous version of the logarithmic function. So let me do that. You can see it's fairly easy. Well, certainly we also know, by the way, that natural logarithm of e to the 1 is equal to, well, remember they're inverses of one another. And since they have both the same base, I just get the input, which is 1 in this case. So I get 1. So therefore, I can rewrite this expression for the logarithm base e, or the natural logarithm. In particular, I've got d dx of, well look, this becomes, if I put base e in here, it's natural log, so natural log of x, is equal to, I use this exact same formula, except, of course, log b is equal to 1, right? Because log of e, right? If I replace b with e, I get 1. So I get 1 over 1 multiplied by x. So of course we don't usually write 1 multiplied by x, we just write it as x. So in fact, now I have the expression for the derivative of the natural logarithm. Okay? So we have the derivative of all logarithms, the natural logarithm, and of course logarithm base b. Right? These are the two shortcut rules for differentiating logarithmic functions. So now let's summarize these derivatives. Here's the derivative shortcut rules for logarithmic functions. That is, the derivative with respect to x of log base b of x is 1 over log b times x. And the derivative with respect to x of the natural logarithm of x, that's logarithm base e, is just 1 over x. So notice they're exactly the same. This is certainly more generic or more general than the logarithm base e. And so we can do some examples. That is, here I've got f and g defined as, well, logarithm base 5 or natural logarithm. So if I compute the derivative of f of x with respect to x, just go ahead and use the formula. Notice that in this case, it's just log base 5, and so my b is 5. So the answer here is just going to be 1 over the natural logarithm of 5, whatever that number is, multiplied by x, right? That's the derivative. And similarly, the derivative with respect to x of my second example here, g, well, it's just going to be 5 multiplied by the derivative of log x. Remember about properties of derivatives. That is, if I just have a constant multiplied by a function and I take the derivative, I just ignore that constant and multiply that by the derivative of that second function, right? So the derivative here is just going to be 5 multiplied by the derivative of log x, right? Well, the derivative of log x is 1 over x, so I get 5 times 1 over x, or 5 over x. Now we can easily extend these definitions to an even larger class of functions using the chain rule. So since we already know these two derivatives, let's extend this further. Okay, so what if I want to know the derivative of log base b of f of x? Maybe I've got some function inside of there. Okay, again, I can just use the chain rule. Same thing for natural logarithm. So again, I'm going to use the exact same expression, except now, remember that when we're using the chain rule, or when we're thinking about chain rule, we have to sort of treat it like an onion. We differentiate the outside part and multiply that by the derivative of the inside part, right? So in this case, well, the derivative of log base something is just this thing, right? Except the something is the x. So in this case, what we're going to get is 1 over the natural logarithm of b, yet that didn't change. Except the difference is that there's that inside bit, right? So I'm just going to call that f of x. That's something I'm talking about. That's the derivative of the outside part. But then I have to multiply that by the derivative of the inside, which happens to be f of x. So there's an f of x prime. Okay? And similarly down here, I'm going to go ahead and use the chain rule that we know about, except now my input is called f of x, not just x. Okay? So the derivative of the outside part is 1 over whatever is the input. In this case, I call it f of x, not just x, multiplied by the derivative of the inside. And of course, the inside is called f of x, so we multiply that by that derivative. Okay? So now, just using the chain rule, I've extended these definitions to a much bigger class of logarithmic functions. In fact, let's sort of write this down in a more coherent way. A better way to write this is just to write f prime of x on top. And similarly here, this is just going to be f prime of x over f of x. So these are the shortcut rules for logarithmic functions. Let's actually go one step further in generalizing what we've just talked about. Okay, so in particular, these are all the shortcut rules that we could come up with for any kind of logarithmic function, whether it has just x as an input or some kind of a function of x as an input, right? These are, of course, the more general version, and in fact, these are more specific to these, okay? That is, that if f of x happens to be equal to x, you're just going to get these, okay? So these are the most generic rules down here. But I want to extend things just a little bit. So certainly you know that from algebra, the logarithmic function has a domain that goes from 0 out to infinity, right? We can extend this even further if we think of the logarithmic function having an input with an absolute value in there. So usually what we do is extend things so that our domain increases to everything except 0, right? So that means that I could extend these definitions by thinking of this as an absolute value on the inside part. And this way, we can make these functions even larger, right? Or in other words, we can do more with them if we think of these with an absolute value for the input.